Hello, welcome back. In this video, we're going to go through an exercise to practice the sigma notation to represent the sums. And in particular, we have the sigma, the sum of I squared minus I plus 1 for I equals 1 all the way to 11. But at this moment, I want to step back and I want to remind you what this sigma notation stands for and how we handle this problem. So here is a few words of the sigma notation. Here you have the sigma sign here, as you see, that represents the sum. And you have the I running from 1 to n. We're going to call it the index of summation. And we're going to call all of these terms to be AI. So AI is the ith term for that reason. And these are the upper and lower bounds of the sum. So I starts from 1, goes all the way to n. So the lower bound is 1, upper bound is n. And you're adding all AIs. So it's essentially the shortening the sum notation here, because if you have a million terms, you don't want to write it down all the way to million, A1 plus A2 plus A3 all the way to A1 million. You represent that by the sum here. You just say like I starts from 1, goes all the way to 1 million, and this is just still AI. And we have summation formulas, and these are pretty nice, in fact, to know. So if you add C's, a constant C, to itself n times, in other words, that is equal to C plus C plus C all the way n times. Okay. This rule says that the result is going to be C times n, as you see, because I'm adding them C times n is the answer, obvious answer. Okay. And the second rule says that if you're adding i's, and i's from I starts from 1, goes all the way to n. In other words, for I equals 1, I is 1, right? And then the next term is going to be 2, because I becomes 2, and then 3, and let's say you go all the way to n. So you're adding numbers starting from 1 all the way to n you determine. So that sum is essentially equal to the last term, last index here, right? Times one more of that divided by 2. So let's say if you're adding numbers 1, 2, 3, 4, 5 all the way to 100, that sum is found by a formula. It's 100 times 101 divided by 2. And then this one is all about having a good formula for sum of the squares of numbers starting from I equals 1 going all the way to n. And it's n plus 1 to n plus 1 divided by 6. And we also have a formula for sum of the cubes of the numbers starting from 1 all the way to n. So it's n squared, n plus 1 squared divided by 4. Going back to our example here, so we have the index starting from 1 going all the way to 11, and we're going to look at the sum of this whole term here. Why don't we split this sum into smaller sums, because once you write down the sum of numbers, you can always rearrange them as long as this sum is not infinity here. As long as you don't have, in other words, infinitely many terms added, but just finitely many of them, so you can rearrange the terms like this. Okay? And for each of the pieces here, we have a formula listed in the previous slide. And remember that the upper bound is always 11 here, and the lower bound is always 1 here. So this is going to be equal to, so this is our n, okay? So it's n plus 1, and 2n plus 1, so it's 22 plus 1, divided by 6. And here we are adding just numbers, so this is in the form of I, so we still have a formula for that. It's n times n plus 1 over 2, so it's 11 times 11 plus 1 over 2. And for this one, we have 11 times 1, 11 times this constant, because you're adding ones 11 times, so you get 11 times 1. Okay? You can simplify these terms. So 22 times 23, and then this is going to be 6 times 11, or 11 times 6, and the other one is going to be just 11. It turns out that the sum is 451, and we can go ahead and then just say like this is equal to 451.